So in this module, we will look at the protected mode of operation of the x86 processors. So far, whatever we have seen from module 1 to module 4, we assume that 8086 or 80286, 386, 486 are all working in the real mode of operation. So what we will attempt in this session is to see the difference between the real mode of operation and the protected mode of operation. Now we know that if we are working in real mode of operation, only the first 1 MB of memory is going to be accessible. This first 1 MB of memory is what is called as the real memory, or another term that is used to describe this is conventional memory. And generally, if your operating system happens to be DOS, it can access only the first 1 MB of memory, or the real memory or the conventional memory. Now, if you're talking about 8086 or 8088, they have only a 20-bit address. Having a 20-bit address, they can access only 1 MB of memory. As they access only 1 MB of memory, they can operate only in real mode. The concept of real mode and protected mode comes only from 80286 onwards. So when we are talking about 80286, 386 or 486, they are capable of working either in the real mode of operation or in the protected mode. So in real mode, they will behave just like an 8086 system, where they are able to access only the first 1 MB of memory, called the real or the conventional memory. And whenever we try to access the conventional memory, we talk about segments. There is the code segment, there is the data segment, stack segment, extra segment, and if it happens to be 386 or 486, there are two more segments associated, the F and the G segments. So every address is going to have two parts in real mode. There is a segment and there is an offset. And the size of a segment can maximum be up to 64K. The reason why it is 64K is in real mode of operation, the offset will be only 16 bits. If the offset is 16 bits, the size of the segment can be only 2 to the power of 16, which is 64K. So whether it is 8086, whether it is 486, it doesn't matter. If it's in real mode of operation, the offset will be a 16-bit offset that would be considered. Now, the main advantage of segmentation, we have seen this earlier also, is going to be relocatability. So the memory here is physically divided into at least 4 segments. In case of 386 to 486, there can be up to 6 segments, and the maximum segment size will be only 64K. So this is if you are working in real mode of operation, and 8086, 8088, they only work in real mode of operation. So if you are talking about processors higher than 286, the other mode of operation available is going to be the protected mode. So if you want to access more than 1 MB of memory, if you want to go above the first 1 MB of memory, then you have to use the protected mode of operation. Your Windows operating system or Linux operating system, all of them work with the concept of protected memory. Now, when we talked about real memory, we said that there is something called as segment and offset. In case of protected memory also, the address would be divided into two parts. There is going to be a segment and then there is going to be an offset part. But the segment doesn't have the same meaning as in real mode of operation. The offset continues to remain the same, but the segment has a different meaning in protected mode of operation. Address will still have two parts. You will take one part from the segment register, you will take one part from the offset. But here the segment has a different meaning, or the value which is present in the segment register means something else. So what does the value in the segment register mean? The segment register doesn't have a segment value now, rather it has a selector. The selector selects an entry, or it selects a descriptor from what is called as a descriptor table. So there is a descriptor table present in memory. The descriptor table has a list of descriptors. From these descriptors, one of the descriptors would be selected using the value present in the segment register. Segment register has a selector. Selector selects a descriptor from the descriptor table. So what exactly does this descriptor have? The descriptor has the location of the memory segment. It has the length of the memory segment. it also has the access permissions of this particular memory segment. It will say which are the applications that can access these segments. So those are called as access rights. So information regarding the access permissions also are present as part of this descriptor. So segment register has a selector. Selector selects a descriptor from the descriptor table. So segment now means something else in case of protected mode of operation. And instructions will not of course change because you still have the segment offset combo. The segment now means something else, that's all. But still you have segment, you still have offset. There will be a value present in the segment register. There will also be an offset present. So the instructions will not change. And in case of 80386 and 486, you are going to get an additional advantage that now your pointers can be 32-bit pointers. So 32-bit offset is now going to be allowed. Earlier when you were using 80386 or 486, the offset generally allowed was 16 bits whenever you are working in real mode of operation. When you're working in protected mode of operation, you can have 32-bit pointers or you can have 32-bit offset. So how exactly does the whole thing work? Now I talked about selecting a descriptor from a descriptor table. So any system has two descriptor tables. There is what is called as the global or what is called as the system descriptor table. The global descriptor table is common or it applies to all applications or all programs that are currently being executed on the processor. Now, whenever we talk about the local descriptor table, every application has its own local descriptor table, or it might have a set of local descriptor tables. So local is something which applies to a particular program or it applies to a particular application. So there are totally two descriptor tables available in memory. And one is the global descriptor table, which is common for all programs currently being executed. And there is another which is called as the local descriptor table, which is going to be different for every application. So each descriptor table has up to 8192 entries in it. So totally if you have 8192 entries and you have two descriptor tables in memory, there would be at any point of time 16,384 descriptors. 8192 into 2 will be 16,384 descriptors. Meaning that at a given point of time, there can be 16,384 segments because every segment has a descriptor. Now forget the concept of having 4 segments: code segment, data segment, stack, and your extra segment. Those are the physical segments. Now what we are talking about is we are going to be talking about a segment having a descriptor. So if a segment has a descriptor and totally there are 16,384 descriptors, it also follows that there are 16,384 segments available in memory. And what can be the size of every segment? Your offset is allowed to be 32 bits. So if your offset is allowed to be 32 bits, for instance in 80386 and 486, it can be 32 bits. So if your offset is going to be 32 bits, then the total size of a segment can be 2 to the power of 32, that is 4 GB. So every segment can be up to 4 G. So now remember that we say that there are totally 16,384 segments, or we say there are 16K segments. 16,384 is nothing but 16K. So there are 16K segment and every segment can be of size 4G. So it means that virtually I can assume that there is 64 terabytes of memory. 16K segments, every segment 4G. So size of memory becomes 16K into 4G, which is 64 terabytes of memory. Now this memory is not physical because if you look at it from 80386 processor's point of view, your size of the address is going to be only a 32-bit address. So if it is a 32-bit address, physically there is only 4G of memory present in 80386. But then if you look at it from the descriptor's point of view, we say that there are 16K descriptors. Every descriptor can be 4G. So it means that there are 16K segments. Every segment is going to be 4G. Virtually, we say that there is 64 terabytes of memory. So this is what is called as the virtual memory. Physically, this memory is not present because physically you are restricted by the address lines. Address lines are 32 bits. So physically you have only 4 GB of memory. But then you can have 16K segments and every segment can be of size 4G. So it means that virtually when you are writing a program, you can assume that there is 64 terabytes of memory. So there is a mismatch between the virtual memory size and physical memory size. So it means that not all segments would be simultaneously present in memory. Whichever segment is being used by the processor to be executed, only that is going to be physically present in memory. How do these get loaded? It is not within the scope of this module. Later, when we are looking at the operating system, we will then see which segment is physically present in memory and how exactly this virtual and physical gets mapped to each other. We are now looking at it totally from the internal registers and the address point of view. So if you look at it from the address point of view, you have 4K, 16K segments. Every segment is 4G. So virtually there is 64 terabytes of memory. Physically, the address lines is 32 bits. So physically you have 4 GB of memory. So the virtual memory size for 80386 is 64T and the amount of physical memory present is 4 GB. So whenever you talk about protected mode, we will be talking about virtual memory and we will be talking about physical memory. So virtual memory will tell you what would be the limitations for your program size. So the size of my program is essentially limited by the virtual memory. Virtual memory says that my program size can be up to 64 TB. So this is a virtual memory. Physically, the memory present in the processor or the processor can access it at any point of time is only going to be 4 GB of memory. So now in protected mode, we will have two addresses. There will be a virtual address and there will be a physical address. So we will also see how the virtual address gets translated into the physical address. So we will see that in the later sessions. So in this session, what the aim was to just introduce you to the concept of protected memory and talk about virtual memory. So in the next few sessions, we will see how the descriptors work and how the virtual address is going to be converted to the physical address. We'll stop with this in this session.